Lesson 12.5 and 12.6, Angle and Segment Relationships in Circles. The objectives of the lesson are to find the measures of angles formed by lines that intersect circles, use angle measures to solve problems, find the lengths of segments formed by lines that intersect circles, and use those lengths to solve problems. The vocabulary words you're learning today are secant segment, external secant segment, and tangent segment. We'll start with the theorem. If a tangent and a secant, or chord, intersect on a circle at the point of tangency, then the measure of the angle formed is half the measure of its intercepted arc. So if you look at the picture, we have a tangent line. This is the point of tangency B. And we have a secant, AB, and they both intersect at B on the circle. So the intercepted arc, AB, is the part we have to use to find the measure of this angle. The angle is half the measure of the arc. Let's look at an example. Find each measure. So we want to find the measure of EFH. EFH. It intercepts arc FH, so the measure is equal to half of the measure of FH, and all we have to do is plug in the number, 130 degrees, take half of that, and the measure of angle EFH is 65 degrees. Let's find GF now. So we have GF on this side, and we want the arc. Well, this is the angle G, and we see that this is the tangent line, and this side of it is 122 degrees. So this would be a linear pair. The measure of angle G is half the measure of GF. We have 180 degrees minus 122 for this linear pair. So that's half of GF. And that's 58 degrees is half of the measure of the arc. So to clear the fraction, we multiply both sides by 2, and we get 116 degrees. So the measure of arc GF is 116 degrees. Our next theorem talks about secants or chords intersecting. So if two secants or chords intersect in the interior of a circle, then the measure of each angle formed is half the sum of the measures of the intercepted arcs. So since this intersects inside the circle, we have two arcs that we have to think about. And they're unequal because you can see that our secants, our chords are unequal as far as where they intersect. So the measure of angle 1 is equal to 1/2 arc AB plus arc CD. Let's look at an example. Here we have our picture, and we want to find the measure of angle AEB. And that's equal to 1/2 of the measure of AB plus CD. So we plug in the 139 and 113, add them together, and divide by 2, and we get 126 degrees. Theorem 1153 has three pictures, you'll notice, because it's the three different situations you can have. We have a tangent and a secant like we saw before, but instead of being on the circle this time, they all intersect outside the circle. So this would be a tangent and secant, this would be two tangent lines, or in green we have two secant lines. And the theorem states, if a tangent and a secant, or two tangents, or two secants intersect in the exterior of a circle, then the measure of the angle formed is half the difference of the measures of its intercepted arcs. So in this case, we have this distance outside the circle. We need to make up for that distance by subtracting. So we always take the largest arc and subtract the smaller one from it. Let's look at an example. Find the value of x. X is this angle, CEG, and 7 degrees goes with arc DF, and 87 degrees goes with arc CG. Here we have x degrees again for our angle, 74 degrees for the minor arc, and we have 20 degrees for AD. So in both of these, x is equal to 1/2 the difference of the two arcs. We put in the numbers and take half. So x is 40 degrees. For B, we plug in 274 respectively, take half of that, and we get 63 degrees. This would be an application, much like what you'll see on an EOC. In the company logo shown, the measure of arc FH is 108 degrees. The measure of LJ is 12. What is the measure of angle FKH? So we start with our formula. We know that the measure is equal to half the measure of FH minus LJ. We plug in those numbers that they gave us, even though they're not on the picture, and we get 48 degrees. This is an overview of all three of those theorems, and you can just remember them this way. On the circle, half the intercepted arc. In the circle, half the sum of the two arcs. Outside the circle, the difference of the two arcs, divided by 2, of course. They all have the 1/2. This one's a little bit trickier. It's a two-step problem, finding the measure of arc YZ. Step 1, we have to find UY. We know that YXV, or VXY, whichever way we want to say it, is 49 degrees. But it has to be measured by the two arcs. If a tangent and a secant intersect on a circle, and yes, that was supposed to be a circle, but my PowerPoint doesn't like that symbol, at the point of tangency, then the measure of the angle formed is half the measure of its intercepted arc. So we use XVY is 1/2 of the measure of UY plus WZ. And this is because we have this side here, and we can easily find this measure. This is a linear pair, so we just subtract 180 minus 113. Substitute 180 minus 113 for the measure of XVY and 68 for WZ. And then we multiply both sides by 2 and simplify a bit, and we get 134 equals the measure of UY plus 68. Well, then we just subtract the 68. The measure of arc UY is 66 degrees. Step 2, we have to then find YZ, which is what we were looking for. We have the measure of angle X is equal to 1/2 measure YZ minus UY. And we substitute in our values. Now we know that this is 66 degrees. And multiply both sides by 2 and add 66 to both sides. So the measure of arc YZ is 164 degrees. Let's look at the chord-chord product theorem. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of those chords are equal. So I would multiply CE times ED, and that would equal AE times AB, or EB, excuse me. Looking at an example, if we want to find the value of X and length of each chord. So EJ times JF is going to equal GJ times JH. So 10 times 7 will be 14X. We divide and we get that X equals 5. Then to find the lengths of the chords, we just add up the separate lengths. We have EF, goes straight across this way, and it is 7 and 10, so that would be 17. And GH would be 14 and 5, so that would be 19. A secant segment is a segment of a secant with at least one endpoint on the circle. An external secant segment is this part of the segment that lies outside the circle with an endpoint on the circle. So we have PN and NM, KJ and JM. They're all secant segments. The external ones are these, NM and JM, because they lie outside the circle. This brings us to the secant-secant product theorem. And basically what this tells us, if we have two secants that intersect at the same point outside the circle, then the whole secant times the outside part of one is equal to the whole secant times the outside part of the other. So AE times BE equals CE times DE. And let's look at an example of that. On the value of X and length of each secant segment, well, it's the whole times the outside, so we have to add these up. And for DE, we have 16, and we multiply that times the short part outside, 7. And then we add these. We don't know what X is, so we say X plus 8 times 8. And then we solve for X, and X equals 6. And to find the length of each secant, we simply add up the pieces. So ED would be 16, and EG would be 14. A tangent segment is a segment of a tangent with one endpoint on the circle. So AB and AC are tangent segments. The secant-tangent product theorem lets us take that part of it and say that the whole times the outside, like we said before, equals the tangent squared, because the tangent is the segment is smaller. So we have AC times BC, that equals DC squared. Let's look at an example. We want to find the value of X. and x is our tangent segment. So we will take the whole of the secant, so that would be 20, multiply it times the outside part, which is 5, and that will equal x squared. So we have 100 equals x squared, and we take the square root, and x is plus or minus 10. However, the value of x has to be positive because it represents a length. Now you try.